Okay guys, what we're going to do in this set of notes is we're going to go back and we're going to look at what a definite integral, how that might change how we approach this U substitution rule. Now, basically, the beginning part of it is actually exactly the same. So that your first step in doing a definite integral is to actually compute the indefinite integral. And that really has not changed. So we're going to start this process doing exactly the same thing that we did in the practice videos on indefinite integrals by identifying the u with the inside function, calculating its derivative, and then determining whether we need a corrector or not, a corrector constant, and then going ahead and doing the u substitution and thinking about what the antiderivative is. However, there are going to be two ways to deal with the evaluation step. And I will tell you that I'm going to show you both ways in this first example, but I'm pretty much going to go with option 2, and I'll show you which one that is, mostly because we want to be very careful about linkage errors in this. So let's take a look at our definite integral that we have here as an example, and we're going to kind of work through that. So the beginning part of this is not going to change, all right? So I'm going to first identify my inside function, and I'm going to write this over on the side so that it's out in its own little thought bubble. So my u would be the 1 minus 4t cubed. I'm going to go ahead and take the derivative and put it in differential form, negative 12t squared dt. And so basically, I'm just going to kind of put that up here in a thought bubble, I can identify whether I'm missing anything or if I need a corrector in this. And since we notice that we have a minus 12t squared here, but yet over here I only have a 2t squared, I am going to need a corrector. So we're going to have to add in, we're missing at least, we need a negative 6. So my corrector on the outside, because remember we want to multiply these to get 1, we're going to put a negative 6 on the inside, and we're going to put the negative 1/6 on the outside as my corrector. So we're going to come down here in the problem, we'll do equals. I'm going to put my integral, negative 2 to 0. I'm going to go ahead and start formatting this a little bit better for getting ready for the derivative, 2t squared dt. Now, when I'm looking at this, and let me just move this, oops, I'm just moving this over so I have a little bit more room here. We'll just kind of come down here. So I'm going to add in that corrector that I need. I need an extra, so I'm just going to kind of do this. I'm going to multiply this by negative 6. And that means I need to put a negative 1/6 on the outside. So that's kind of setting it up and ready for us to do our U substitution. Now, what's going to happen in the next step is where we are going to kind of break into two options. Now, one option, once I get it written like this, is to recognize that we already have the antiderivative, or we know what our derivative is. Because this stuff that's on the outside, I'm just going to highlight it, that's part of the derivative of the stuff, the derivative of the inside function. So we're going to ignore that now that we have that correct. So we can kind of in our head not actually do the U substitution. So this is the not do the U sub. We just kind of think about it in our head, but we don't actually do it. All right. The second option that we have over here is going to be to actually do the U sub. Now, I'm going to tell you, I'll put a star by this one because that's going to be by far my preference, because I think it's a little harder, especially for when you're in the beginning of doing integration, to be able to do this without revealing the known derivative and then taking the antiderivative. If I do it without doing the U sub, I would come down here and I would be like equals negative 1/6. And in my head, I have to remember that I am doing the antiderivative of stuff to the 1/2. So I know that I'm going to take that stuff, add 1, to my power and then divide by that over here. And it's a definite integral, and we're evaluating that from -2 to 0. So we find that antiderivative. But notice that in this method, everything is still in terms of t. And so then I would continue, and we know that what we're going to do is we would plug in the 0 first, and I will simplify kind of as I go. This would be negative -1/9 because of simplifying the fraction. I'm going to plug in 0, and it would become 1 to the 3/2. And then we subtract, and now we do want to be careful, our -1/9. And we plug in -2, so it'd be 1 minus 4 times -2 cubed to the 3/2. I have a tendency, I like to put parentheses around that one, especially when we're doing this complicated substitution step. You need to watch for errors in negatives as you are doing these types of problems. So this would end up being -1/9 and then plus 1/9 times, this ends up being, I believe, 33. So 33 to the 3/2. And we'll leave it like that in these terms. Now, one of the things that you want to notice, like in this technique, one, it requires you to have very good visualization skills on what we're doing for the sorry, I got distracted because I was trying to look at having a little bit of a technical difficulty here. Okay, so now that I fixed that, coming back, what I'm basically looking at here is that when we did the substitution, you kind of have to understand the antiderivative as you go. You're visualizing it in your head. You're trying not to make careless errors. You're making sure you apply the antiderivative rules correctly. And so this is not my favorite choice. But I do want to point something out to you that as we're looking at this, okay, if you have a definite integral in the beginning of the problem, one of the linkage issues that you have to pay attention to is it must be a definite integral through the entire problem. So you must have bounds here and you must have bounds here, okay? So you can't go from suddenly being a definite integral to treating it as an indefinite integral and not putting bounds. You must put the bounds each time to show that you know that you're doing a definite integral until you get to the FTC, right? Because down here, this was by FTC, where we were allowed to plug in and calculate our net change. Now, I'm going to do the next way is going to be the far preferable way, which is the going ahead and doing the U substitution. All right, so now taking a look at that, we're ready to set this up now. We're ready to say equals, and we're going to do the U sub. So that's -1/6. Now, I'm going to start by not writing the bounds. I want you to hold your thought on what the bounds are going to be. We would make this u to the 1/2 du. I like this because it reveals what I am taking the antiderivative of very clearly. Now, the problem with this is that it has to be a definite integral. And I can't write 0 and -2 as my bounds because 0 and -2 are not u values, they're t values. And so the rule is that when you switch to u, everything must switch. Everything has to change to u, even the bounds. And so that requires a little bit more work in this step. But it's actually okay because we did the work in version 1. We just did it at the end. So it doesn't really matter when I do it, and I think this is much clearer. So you would make a note to yourself, and you would say, well, x equal to -2, that's my lower bound. I would use the rule that's up here, right? We have a rule for how we're finding u up above. So we plug in -2, so we have 1 minus 4 times -2 cubed, which is the 33. Notice that it matches what I did at the end over here. So we're kind of front-loading a little bit of that arithmetic that's there. And then x equal to, my other bound was 0. If I plug that in, 1 minus 4 times 0 cubed is 1. So what's going to happen now is we're going to change the bounds. The bounds have to be in the same variable that you are doing. So the negative 2, which was the lower bound, is going to become 33, and the upper bound is going to become 1. And no, I don't really care that they don't go from smallest to largest. You just put in what they have. Now, at this point, we would do the antiderivative, which would be our u to the 3/2 times 2/3, following our power rule. And we're evaluating from 33 to 1. And then I plug in negative 1/9. That's the simplifying the coefficients at the front. And then you just go 1 to the 3/2 minus negative 1/9, 33 to the 3/2. And do you see how it's much cleaner down here at the bottom because we kind of front loaded our arithmetic? So we get our negative 1/9 plus 1/9, 33 to the 3/2, and we have the same answer. But I will tell you that I do far prefer that version of the method of doing it. Go ahead and do the u substitution, change everything into u, and then calculate your antiderivative. I think it makes it much clearer. Okay, so keeping in mind that while they're both valid solution methods, we're going to use the second pretty much exclusively because I think that makes the evaluation step easier and you guys don't have linkage errors. So I'm going to try to fit 2 examples in this video right here. So let's take a look at the first one. I'm going to identify my inside function. My u is going to be 2w plus w squared. My differential form du is going to be 2 plus 2w. We examine what we have here, and we see that we're missing a 2, so we need a corrector. All right, we're going to add that in. So in this step right here, I don't need to change the bounds because I'm still kind of in my w variable. I'm just setting this up, 1 plus w dw. I add in the missing 2 that we have here. I correct on the outside. And then I go ahead, and at this step is where we're going to do the second portion, which is calculating our bounds. We're going to switch to u. I initially leave the bounds off, so I got u to the 5th du. Do not forget to put them on there, though, because when you are doing this, if you do not put the bounds in, that would be a linkage error. So now I'm going to come over here, and I'm going to calculate when w is negative 1, and I'll leave the arithmetic up to you, but u is going to end up being negative 1 also. When w is equal to 5, then the u ends up being 35. So I will leave the arithmetic to you, but make sure you do that. We add that in, negative 1 to 35. We calculate our antiderivative, so u to the 6th divided by 6. Evaluated for negative 1 to 35, and we plug and chug. So I have 1/12, 35 to the 6th, minus 1/12, negative 1 to the 6th. And at that point, I'll stop because the arithmetic is not something that we want to worry about. All right, now let's take a look at the second one here. And the reason that this is in here is because sometimes you have to use integral properties. So you have to watch for that. Now, in this problem, I'm going to recognize that I have a couple of things here. I have constants that are going to be riders. You'll see why in just a second. I also see that I have a subtraction in here. And so kind of thinking ahead to where we're going to go with this, I'm really going to rewrite this as 4 definite integral negative 2 to negative 6, 1 over 1 plus 2x cubed dx, minus 5, negative 2 to negative 6, 1 over 1 plus 2x dx. So I use the properties to rewrite that. All right, now once you've done that, why don't you guys go ahead and try the u substitution and then come back in a few seconds. I'm going to pause it, and you pause your video and then come back and check your answer at the end. All right, go ahead and check your answers to this in our last few seconds in this video. Notice I added a corrector into both of these. I changed my bounds so that everything was in terms of u. I found each antiderivative. Now be careful. I'm also going to tell you negative mistakes are the biggest problem in these. So make sure you include these parentheses there. All right, well, you guys do the last two.